Dr. S. Ramalingam, Joint Registrar Phase 2, Dr. S. Manivanan, Dean Phase 2, Dr. Rajavarman, Deputy Dean Phase 2, Dr. P. Udayakala, Dean Chemistry, and Dr. S. Valiamai, HOD Chemistry. Our institution continues to travel in a successful path under their constant guidance and support. The faculty members of our department are well trained in teaching as well as research and shines with maximum doctorates. The curriculum is designed so that the incumbent can excel in their subjects and can clear various competitive exams like NET, SLET, and so on. The alumni are placed in higher positions in various organizations. Our vision is to support and advance the learning, teaching, and research activities by creating a workplace environment that encourages development of professional and personal growth and integrity with responsibility towards health, safety, and environmental protection. Our mission is to encourage students to be more creative, inquisitive, and to understand the technology based on chemical science concepts, and to make students imbibe the value of interdisciplinary thinking by providing them with educational and research opportunities in application-oriented chemistry. Courses offered: undergraduate courses for 3 years, BSc Chemistry, BSc Industrial Chemistry, BSc Medicinal Chemistry, and BSc Applied Chemistry. Postgraduate courses for 2 years, MSc Chemistry and MSc Nanochemistry, and research programs, MPhil and PhD. The key highlights of the program: competitive curriculum, exposure to sophisticated instruments and chemistry software, well-equipped departmental library, excellent teaching with modern methods, co-curricular and extracurricular activities, well-qualified, experienced and dedicated staffs, project-based learning, industrial visits, placement cell to guide the students for campus placements, excellent main library with e-learning and e-journal facilities, separate hostel facilities for boys and girls equipped with gym, study room, TV hall, etc., transport facilities, and Wi-Fi enabled campus. Highly equipped UG and PG laboratories are available for the students to deepen their knowledge in theory and procedures in various experiments. The computer-based Chem Informatic Lab is equipped with advanced software to help students to work with molecular modeling simulation. The Chemical Analysis Lab is equipped with all necessary equipments like corrosive resistance, digital balance, hot air oven, and so on. Well-equipped smart classrooms with high-end projectors facilitates our teachers do interactive teaching methodologies and the students to learn advanced techniques. Our institution boasts of best-in-class infrastructure with excellent and well-designed classrooms. Each classroom is organized with a spacious atmosphere to make the learning experience enjoyable. The department has a library comprising over 500 books. It is inbuilt to facilitate students to have subjective learning and discussion with faculty members while studying. The department organizes various events like symposium, conferences, guest lectures, workshops, webinars periodically to make the students to expertise beyond regular classes. Eminent personalities from industry and academic institutions are invited to share their knowledge and experience. Our students are encouraged to participate in national and international conferences and are given opportunities to put forth their ideas in research. The department organizes a project expo every year to assist students in showcasing their hidden talents and knowledge in chemistry in the form of activities and explanations. Our students actively participate in various NSS activities to help improve their personality through community service. Institutional social responsibility events are organized to inculcate social awareness, values, and environmentally responsible behavior among students. Industrial visits to reputed industrial organizations are arranged regularly to enable our students to have a wide exposure to practices followed and goods manufacturing processes such that they gain deep knowledge in industrial and applied chemistry. In addition to academic events, Cultural Fest is also organized by the department to help students to stage their talent and get recognition on a greater scale. In order to bring our students closer to traditional and cultural beliefs, various festivals are also organized and celebrated by the department. Convocation ceremony is held every year to give an opportunity to our graduated students to share the celebration of their accomplishment with their peers, family, and friends. To make our students more energetic and strong, and to make the academic sessions more interesting, our college celebrates Sports Day every year. Various outdoor and indoor games are conducted for a period of 1 month, and the winner and the participants are honored on the Sports Day. For more information, please visit our university at Madurai, Chennai. Visit our college website www.drmgrdu.ac.in. Follow our Facebook page at MGR University Deemed and our Instagram page, Chemistry FHS Dr.MGR ERI. Thank you.
A very good afternoon to all. I'm Dr. R. Nitya, Assistant Professor, Department of Chemistry, Dr.MGR Educational and Research Institute. It gives me immense pleasure in meeting you all for the fourth day of FDP on challenges in chemistry and its applications towards energy resources. In this studio, we have our Deputy Dean, Dr. B.N. Rajavarman, and our today's speaker, Dr. J.Selvakumar, and Head of the Department of Chemistry, Dr. S. Valliammai, and my dear colleagues, Dr. L. Ramapriya and Mrs. M. Jeevaratnam, Assistant Professors, Department of Chemistry. Now I call upon our HOD, Dr. S. Valliammai, to deliver welcome address.
Yeah, good evening to one and all gathered here for this FDP conducted by the Department of Chemistry of Dr. MGR Educational and Research Institute. I am extremely glad to propose my welcome address on behalf of the management and the organizing team. I render my warm welcome to the dignitaries, our Chancellor, President, Vice Chancellor, Provost, Pro-Vice Chancellor, Registrar, and Joint Registrar of H&S. I also welcome the dignitaries of our campus, our Joint Registrar, Dean, Dr. S. Manivannan, who always encourages us in conducting such valuable programs. Our Deputy Dean, Dr. V. N. Rajavarman, who is a man always on heels. He always supports us, lights, and encourages us with innovative ideas which can be brought into reality. I am very much happy for gracing your presence in this occasion. I welcome you, sir. I feel very proud to have our today's resource person, Dr. J.Selvakumar, Scientific Officer from BARC. He is a man of energy, just like the energy released during nuclear fission, vast knowledge and experience in the field of research. He is a powerful person, just as a nuclear power plant. His speech will be a scintillating spark to all of us. We welcome you, sir. I also welcome my dear staffs of my own department who are always along with me and support me in all needs. I welcome you all. I also take this opportunity to welcome our today's participants without whom this FDP would not have happened. I hope you all will enjoy and gain knowledge about nuclear waste management. An important announcement: feedback link will be provided tomorrow on the last day of FDP after the session gets over. You can post your queries in the chat box and it will be clarified after the session. Thank you. Once again, I welcome you all.
Thank you, ma'am. Now I call upon our Deputy Dean, Dr. V.N. Rajavarman, to felicitate the gathering.
Good afternoon to one and all. On behalf of Dr. MGR Educational Research Institute and our young, eminent and dynamic personality of our President, Engineer ACS Arun Kumar, I would like to thanks to our today key speaker, Dr. J. Selvakumar, Scientific Officers, Department of Atomic Energy, and also personally, I thanks to for accepting our invitation on this FDP, national level FDP on challenges in chemistry and application towards energy resources. And I wish always the Department of Chemistry, the head of the department, Dr. Valli MI, and my dear faculty of chemistry, and all the participants for arranging, for organizing this wonderful FDP by online. Particularly, I wish Dr. Ramapriya and Ganesh Babu for giving excellent technical support on this running FDP today. Once again, I wish all of you and success the event in grand manner on today. Thank you very much.
Thank you, sir, for your address. I now call upon Dr. L. Ramapriya to introduce today's speaker, Dr. J.Selvakumar.
Good evening to one and all. I'm very much delighted to introduce our resource person for the day. Dr. J.Selvakumar is a scientific officer in Baba Atomic Research Center. He is assistant professor in Homi Baba National Institute, Kalpakkam. J. Selvakumar obtained his PhD in chemistry in the year 2010 from Loyola College, University of Madras, India. Following 1 year of Indian prodigious KSKRA fellow at the Department of Atomic Energy, Baba Atomic Research Center, Dr. Selva joined BARC as a scientific officer in 2011. His research interests are chemistry of CVD precursors, thin film deposition, thermal studies, and nuclear waste management. He has penned a book on thin film deposition. He has 32 international publications that include American Chemical Society and RSC, Royal Society of Chemistry. He backs more than 50 national and international conference papers. He is a life member in various scientific societies like Indian Carbon Society, Indian Academy of Science, and Society of Material Science. Sir, we are very happy to have you for this faculty development program. I'm sure your talk is going to help in molding and developing the career of all faculty members in this gathering. To all the participants, kindly post your suggestions and questions about the session in the chat box. The questions will be answered at the end of the talk. So don't worry about your certificate. The details about it are given in the description box. Not taking much time, I invite our speaker and hand over the session to him. I invite you, sir. Welcome, sir.
Thank you, ma'am. Thank you very much, ma'am, for the warm welcome. I'm also very much happy to be here, actually. I'm take this opportunity to thank Valiamai madam for inviting me for this wonderful occasion to share whatever I learned, whatever I know about the nuclear and nuclear waste management activities. I thought actually I'll be going to discuss with the students, but now only I came to know that it's a staff-oriented faculty program actually. Still, I feel very proud actually. Thank you very much, ma'am, and all the organizers. Thank you very much. So, what I will talk about nuclear waste management. So, before that, I want to confirm whether my audio is hearable. Anyone can answer, ma'am.
Yes, sir, you are audible, sir.
My audio is hearable?
Yes, sir, you are very much audible, sir.
Okay, thank you, ma'am. Then I will continue. So actually the topic of presentation is nuclear waste management. Nuclear waste. So everyone maybe fear about the nuclear. If the word comes in everywhere, actually nuclear means, oh, that is maybe very fear, will be very dangerous one. But if you see in Kalpakkam or Bombay, in all over the world as well as India, recently 2 weeks before we have achieved one 700 megawatt nuclear power reactor criticality. It went on critical. So people are working even face to face kind of thing. Even more than a 50 to 70 years we are working in the nuclear reactor field. If you talk about the waste means actually it's combined of lot of radioactive materials. So we are handling day by day. So no need to worry about the nuclear. But only thing actually, when the for example, when the corona comes, so we discussed ourselves. So what are the things we are following now? For example, keep the distance and keep clean, as well as uh, how much is possible you have to finish the work. The same thing we are following in the nuclear waste management activities as well. So how much time you are spending in near to that waste nuclear waste, so that much you will get affected. So what other work is there, we have to finish as much as possible, as well as after the work we have to cleanly wash our hand, we have to check our hands, hand monitor, all the monitors will be available with us. So what I'm trying to say actually, so we are practice it. So when the COVID comes, actually for us is little bit okay with us. So similar way, no need to worry about that. Like for now, also people are saying no need to worry. The fear only the factor. So same thing applicable to nuclear as well. So fear factor. So we don't have any fear factor about nuclear. So the nuclear waste, how it is and where it is and how it is generating. So what is the nuclear waste? So for example, if I say we are taking a banana day by day, daily we are taking it. So there also radioactivity is there. So radioactivity is called potassium 40. That is radioactive element. So we are taking it. So the normally available radioactive element, for example, even in our houses also radioactive things are there, like radon in your granite or wall, everything is generating some radioactive elements, radioactive isotopes. So everywhere radioactive is there, but only thing in compared to surrounding in our nuclear reactor, nuclear waste management areas, that activity little bit higher compared to outside world. But we should have a protective things. So we should take care of properly, then we'll smoothly works. So first we'll so how what I planned this presentation, how want to discuss about this presentation is, so what is the nuclear waste and where it's generating, and as well as the mainly the generation of nuclear waste, waste, which means the fission reaction, where the energy comes, energy is the product, and the nuclear waste is the residue. We can say in the chemistry point of view, this is a residue. The residue also we no need to throw just like that. We can't throw, but if I am doing some synthesis in the chemistry laboratory, the one product comes, the residue I can just like that dump it, like we can wash it out in the sink or something. But it's not possible in the nuclear sector. So after the energy, electricity produced, whatever comes out, we have to carefully manage it. For why I'm saying carefully manage it, for example, nuclear waste. So maybe you will wonder, actually all the hospitals in India, not only in India, all over the world, hospital is generating some amount of radioactive waste. So how? For example, a cancer patient. The patient is given by radiotherapy. For the radiotherapy, cobalt 60 radioisotope is used. So radioisotope cobalt 60 is having an off-life of 2 hours, 2 years to 5 years. So after that, the all cobalt 60 will not be converted to other element. So it will having some radioactive element. The effect of radioactive should be there. So we just like that throw out of our house. So we have to carefully manage it. Manage in the sense, we have to immobilize. We have to vitrify it or immobilize somewhere that should not affect the human race. Okay, similar way. Now nuclear waste, first we'll start with that the generation of nuclear waste. For that, we should know about the nuclear fuel cycle. Okay, nuclear fuel cycle is a cycle. So in internationally, that cycle is classified as two way. One is open, one is closed. So this depends on the availability of fuel. For example, if you take India, we don't have a resource, but we are having a resource of thorium. but thorium will, that for the technology still we have not started. So we should have a uranium 235. So maybe I'm saying a number, uranium 235, chemistry, everyone chemistry teachers surely will know about that. Uranium 235, what is the role? Uranium 238, what is the difference? These are all uranium isotopes, right? So uranium 238 and uranium 235. So uranium 235 is fissionable, uranium 238 is fertile. So which means actually that uranium 235 is required to generate electricity. So uranium 238 also is required to generate other fissionable element like plutonium, right? So now we don't have a resource. India don't have a resource. We have to import from foreign countries. For example, Australia is having a sufficient amount of, maybe a lot of amount of uranium is there, and Kazakhstan, a lot of country. So we are getting from the foreign country the uranium fuel. So we have to install it. Like for maybe we are, for example, we are having almost now 23 nuclear reactor in India, right? Including last 2 weeks before that Gujarat nuclear reactor not critical. That is including 23 nuclear reactor is there in India. For the 23 nuclear reactor, so we have to feed the fuel first, right? So after that, so maybe one time if you feed the nuclear fuel into the reactor, it will be comes to almost 4 to 5 years. So after that we have to take it, then we have to feed with a new fresh fuel, right? So we should have a fresh fuel abundantly to fill it. For example, if we take some other countries, for US if you take, they will not go for reprocessing or reuse of nuclear fuel because they are having sufficient amount of uranium. But for us, we don't have it. So that's why that nuclear fuel cycle is came two different classification, is open and closed. Open in the sense, actually, if you load it and then whatever comes out after the 4 or 5 years, you'll take it and dump it, which means it's a dry, you keep it as you store it as dry, otherwise you make it as some kind of in the canister and put it in the deep geological repository. Okay, that is one way, that is called open fuel cycle. The closed fuel cycle, in the sense, we have to take the spent fuel out of the reactor and reprocess it. Reprocess in the sense the valuable materials, right? The valuable material in the sense actually uranium and plutonium. Apart from that, if you see the nuclear spent fuel characterization, you will have all the element in the periodic table will be existing in the nuclear fuel, spent fuel. So we don't require all the elements. For example, americium is there, cesium is there, strontium is there, all the element like technetium, all the radioactive element as well as in non-active elements, everything will be present in the spent fuel. Now we wanted uranium and plutonium alone, right? So we have to take it. So which means why just like that you burn it everything, so that is also not possible in the reactor. So we will burn it only if I am loading a uranium 238 and plus 235 is 100%. Only about maximum of 5% of uranium will be consumed the 4 years of run. So after the 95% of uranium will be as a waste. So we just like that don't want to put it somewhere in the dump. So we want to take it out as by applying some industrial process to retrieve back uranium and plutonium, and then we'll reuse it in same reactor or some other reactor. It's a similar way. Uranium and plutonium can be separated, and uranium can be loaded into that now normal reactor like pressurized water reactor or whatever thing actually. And other than that, uranium and plutonium can be mixed together and formed as a MOX fuel. So mixed oxide fuel can be loaded into the fast reactors. So reactor is having a different type of reactors, fast reactor, molten salt reactor. So everything having a different type of, the requirement of fuel is also different. So for example, now we are having a Madras atomic power station, right, in Kalpakkam. There we are using a nuclear fuel is natural uranium. So natural uranium, so everyone know about that composition anyway. Natural uranium having a maximum of 0.7% of uranium 235. The remaining percentage will be uranium 238, right? So if I am going for fast reactor or some other type of reactors, maybe 700 megawatt reactor and all, they may require enriched uranium. Enriched uranium in the sense actually that uranium 235 should be there 3 to 4%. Then that kind of fuel can be utilized, give a more electricity, like more generation of efficiency of the reactors, right? This and all, this way only. After that, uranium-235 should be there. So we will, so in this way, that nuclear, after the experiment, after the reactions 4-5 years, the product will be taken out, so that we will be retrieve back of the uranium and plutonium and put it to the reactor, or normal reactor or MOX fuel reactor. Again, after that experiment, we'll take it back and reprocess it and put it into that reactor. This is called, this nuclear fuel cycle called closed fuel cycles. Actually, India is following closed nuclear fuel cycle. So other countries, for US, even France also is following closed one. As per my knowledge, actually, US only is following a open fuel cycle. They are still not started any reprocessing activities or management activities. So now we will start the presentation. Ma'am, can you put that presentation on? Maybe I showed some small overview, introduction about the nuclear, how it is basically generated. So we'll see detailed way, one by one. First, start with the nuclear. You can start, madam, actually. You can start the presentation. Maybe I can say it, actually. So nuclear reactor. So at least 3-4 important components are there in the nuclear reactor: fuel, clad, coolant, and moderator. Fuel, what we talked about now, actually, the fuel is made up of uranium oxide, right? So uranium oxide, natural uranium or enriched uranium. Natural uranium means this is the composition: 0.7% uranium-235, 99.3% is uranium-238, and fraction of uranium-234 will be there in the natural uranium. This is the fuel used in the MAPS, Madras Atomic Power Station, actually. So over that, we are having a cladding material. So maybe you can start here, ma'am, actually. You can start here. This cladding material is called zirconium. So zirconium, you can stop, ma'am. Video can be stopped. The zirconium, now maybe you may remember, maybe a few years back, actually, the Fukushima, some accident has happened, right? Maybe everyone know about that. So what exactly happened? So for example, the nuclear reactor, uranium oxide fuel, like pellets over zirconium tube will be there. Zirconium is made up of completely metal, zirconium, nickel, iron, everything will be there. Some almost 5 to 16 alloys like metals will be combined together and formed as a zirconium. Zirconium having some variations, zirconium 2, 4, and niobium 2.5 zirconium. So we are using presently zirconium 4. So some reason is there for that. First, I will start with that Fukushima, what happened. So when that accident is happened in that water coolant accident, like it's a reaction. So coolant is not available during the reaction. The coolant in the sense water. So it's not available during that accident time. So when that temperature is rising it more and more, so immediately whatever the water, small amount of water present in that, the water metal reaction, maybe everyone studied actually, water metal reactions produce hydrogen, right? When zirconium react with water with higher temperatures, even the presence of nickel is acting as a catalyst to generate more hydrogen, right? So the hydrogen is generated, but that in that situation, actually, they doesn't know, they didn't thought about that the hydrogen may be there in that fuel core. So when they open that core, actually, it's blasted. It's like the big accident is extended because of this hydrogen evaluation. So for that, actually, that is called, actually, zirconium 2 is having a more amount of nickel. So zirconium 4 came, actually, that in the presence of nickel concentration, they reduced it. So iron concentration, they increased. So compared to nickel, iron is maybe less catalytic active material. So nickel, they reduced it. So then some kind of modification after Fukushima accident, all the reactor engineer people are decided to replace in the sense modify the zirconium, or we will coat some kind of stable material on the zirconium. So some kind of material. When I was in Bombay, actually, we have worked on similar kind of projects like silicon carbide coating on zirconium to prevent the water metal reactions at high temperatures, right? Now that uranium oxide, how they will make a fuel bundle. So when uranium pellet will be made, uranium how uranium oxide will be, as you know, actually that mining and milling will be happen. The uranium rich ore will be called rich plenty, and that the rich plenty uranium will be extracted by solvent extraction method. Then uranium will be converted to uranyl nitrate, uranium oxide, right? Uranium oxide. Now you wanted natural uranium or enriched uranium. So if you want an enriched uranium, again you have to go for uranium 235. We have to uranium 235 concentration. We have to increase it. So for that, some technology is there, centrifugation actually. So heavy metal uranium 238 and 235. If you compare, actually 235 a little bit heavier. So when you centrifuge it, actually uranium 235 will be 8 will be comes out of that material, 35 will be concentrated. So that way actually they will enrich the fuel. So after enrichment with the natural uranium or enriched uranium based on the reactor requirement, they will make a pure pellets. Then pellets will be inserted in the zircaloy. Then now you can play VDMM actually. After that zircaloy, all together put it as a fuel bundle. Then it goes to the reactor. So this is a fuel bundle. After that it will be there in the pressure tube. Then it goes to the core of the reactor, right? You can see here. It will go to the core of the reactor. The core will be connected to the primary coolant and secondary coolant. The primary coolant is that water, our MAPS reactor, if you take that water acting as a moderator as well. So I will explain you what is the role of moderator. The primary coolant, secondary coolant, and then we'll have a concrete building. It's a dome kind of structure will be there. So over it, so around 1 kilometer area, you can run the video, ma'am. 1 kilometer area is called as buffer layer. We should not live nearby 1 kilometer because the dose will be higher. So that buffer area will be there. So this is how, so inside of the nuclear reactor will be look like. So over the nuclear reactor core, we are having a control rods. So control rods, what is the role of control rod is actually that you want to run the fission reaction very controlled way. Otherwise, if you take a small reaction, uranium 235 gives some, it undergo fission reaction, it gives barium or krypton plus, so around 150 to 200 mega electron volt plus 3 number of neutrons. So the 3 neutrons again will hit 230 uranium 235. It will be continuous chain reaction. So we should not just like that allow that. We have to controlled way you have to run the fission reaction. So controlled rods are required. So you can see here how the fission reaction is happen in the core uranium 235. It's a fissionable. It's having a 92 proton, 143 neutron. When neutron comes and hits the uranium 235 become uranium 236. When it becomes uranium 236, it will not be stable molecule. So it will be breaks as a part, as a two molecules. So for example, barium 144 plus krypton 189 plus 3 number of neutron will be formed in a single reaction plus energy. And we know that energy will be converted to electricity. The 3 neutron again hits that. Now you can see actually what is the role of moderator. So moderator is the water. So when neutron comes, it will be slow down. If moderator is not there, actually neutron will be passed through that uranium 235. Reaction won't be there that much. So that is the role of moderator. It will slow down that. Sorry, slow down that neutron, and it will be hit that uranium 235. Fission reaction will happen. For example, you can see the comparison. Fission of a single uranium 235 yields a 215 mega electron volt. The 1 mole of uranium 235 gram will give 1 megawatt electricity. Is compared to 1 gram is compared to, you can see 5 lakh gram of CO2 like coal. For example, if you compare uranium and plutonium and coal, so 1 gram will be equal to 1 ton of coal you have to burn it. You can read it in some literature also. So that's how this is a very clean energy. The clean energy we can say, but only thing when maybe we can discuss after that, when we come to the nuclear waste only, little bit problem is there. You can see this is how it will be converted. How much fuel is required, the calculation we can do it. So where we'll get resource? So we can know actually these things are maybe happen. So where we'll get the resource? We don't have it. So we have to go for reprocessing, right? So reprocessing in the sense before, can you stop here, ma'am? So once the nuclear reaction is over, almost 3-4 years, so reaction is over, that it will be taken out and put it into that nuclear font. So it be cool down. So minimum of 5 years. So 5 years cool down. Why we have to cool the nuclear spent fuel? So cooling why is required? For example, when the nuclear fission reactions happen, so it will generate is a numerous amount, numerous amount of radioisotopes. It start with even seconds. It will be converted to some other second. The off life of the radioisotopes will be seconds to the millions years. For example, iodine, if you take actually some of the iodine radioisotopes will be having the fraction of fraction of off life. Something will have some more than a million years. Similar way actually. So that short-lived. So radio isotopes can be classified in the short-lived, long-lived. The short-lived, which means actually the short-lived we can say in the seconds or minutes or days or years also. So less than 30 years we call it as short-lived. More than 30 years we call it as long-lived fission products. So the short-lived, almost 5 to 6 years, that drastically that spent fuel heat as well as the radiation will be drastically comes down. So when the half-life is very short, that radioactivity will be very high. So when that lower half-life, which means the short-lived radioisotopes can be, maybe we can make it as a stable one. So if you cool down, it will convert it to some other element. It's like transmutation. It will convert it to some other element. So you will have a end of the 5th year or 10th year, you will have only the maximum that long-lived fission products only, including cesium and strontium and uranium, plutonium, americium. Those things will be there. For example, cesium 133 is the non-active element. If you see cesium nitrate, if you write actually cesium atomic mass like is 133. So if you go for cesium 137, cesium 134, cesium 135, these things are isotopes of cesium. So in that cesium 135 is having a 10 power 5, that is be more than a million years. But cesium 137 will be the huge amount of cesium 137 will be huge. The half-life is around 29 to 30 years. Similarly, strontium 90. Strontium 90 also similar half-life. These are all the major radionuclide. This will be gives more heat. So after 5 years of cooling time. So strontium 90 and cesium 90, cesium 137. After that, americium 241, plutonium 241, 239, 238, uranium 235, uranium 238. These are major elements, isotopes will be there in the spent fuel finally, right? So after 4 years, 5 years of cooling, in that water, the water will be, the process is not simple actually. The water, they will be daily they will be replenished with a new one. We are having a ion exchanges column to remove whatever comes out of the fuel pond or any leakage is the radioactive. Everything will be that heat whatever generated in that spent fuel will be dissipated or removed from that because of the coolant. You can run, ma'am. Actually, you can start the slides. So after a few years of in that nuclear pond, that spent fuel rod will be taken out as a fuel bundle. For example, taken out of what's the next step of the process is that fuel bundle will be taken to reprocessing plant, right? So maybe some comparison is given here actually scale way. So your 1 gram is this one. So before that, we'll just overview of how the nuclear reactors works. You can see it actually. Fuel rod and water is acting as a moderator as well as coolant. The heat will be generated to that turbine. Then will be generated. Nuclear reaction will be generated. You can see actually. What will be there in the spent fuel? So after 4 years of the nuclear reactors, the spent fuel, the bundle will have almost 95% of uranium, 1% of plutonium, almost 4% of fission products. The 4% of fission products only gives almost 99% of radioactivity to the spent fuel. Because uranium, plutonium, if you see that half-lives are very high, so you will not get more radioactive. So some video you can see here, the same way we are also following here. This is exactly what France is doing it. So after that spent fuel from the reactor will be taken into that as a cost. and will be cooled down in that spent fuel unloading cell. Each by each, we will take it out and cool down and keep it in the pond. So will be like this, will be stored in the pond actually. So next is actually after a few required cooling of spent fuel, that nuclear bundles, we will cut it. I say that cutting also we should have some minimum, some size is there for complete dissolution. So here we will get spent fuel, which means uranium oxide with the fission products, as well as the zircaloy. Whatever we talk about, that zircaloy is a cladding material that we call it as here is a hull. So uranium oxide and whatever oxides formed during the fission reaction, and then zircaloy will be made it as a small pieces. Then those things will be put it into that nitric acid. Higher, almost 8 to 9 molar nitric acid will use it to dissolve. But here uranium oxide, except zircaloy, everything dies. You can see here the dissolution is happening. Uranium, plutonium, and fission products at the form of oxides will be solubilized in nitric acid. It forms some nitrate solutions. Now, so as initially I told, actually we have to separate it. So valuable material here we can say uranium and plutonium. So uranium, plutonium. So here I can say that solvent what we are using it is that called tributyl phosphate. The phosphate kind of solvent we are using, that solvent is more specific to take uranium plutonium from the fission products. So uranium plutonium will be extracted with tributyl phosphate. It goes to some other stream. The fission product goes to some way to stream. Finally, uranium plutonium also will be based on the oxidation adjustment, will be separated. Uranium separately, plutonium separately, fission product separately. This is how reprocessing plant will do. So now uranium plutonium will put back to the reactor anyway. That fission products, that is for further treatments. The uranium anyway, further uranium will be purified. So finally we'll make it as uranium oxide. For that uranium will be converted to ammonium diuranate. That's material called ADU, they will call ammonium diuranate. So ammonium diuranate will be, you can see uranium nitrate recycling. Ammonium diuranate will be called calcine to form uranium oxide, U2O3 or U3O8. Plutonium similar way, plutonium will be complexed with oxalic acid, oxalate. So plutonium oxalate will be against calcine to form plutonium oxide. Right? Plutonium, uranium oxide, one product. Plutonium oxide is one product. So you can see how the precipitation and calcination is happening during the process. So now uranium and plutonium product will be separated. Will be keep it for further use. Same way actually, when you are making a fuel, nuclear fuel, the quality control is very, very important. For example, uranium 238, 235 should be there. So for example, after reprocessing it, so you are having an impurity in the product. For example, americium, if you say americium or lanthanides, these are all predominant fission products. If uranium, plutonium, you are extracting some americium also impurities there or some lanthanide impurities there, that nuclear reaction compared to uranium, lanthanides are more cross section. It will be absorbed more, right? So you will affect the process future. So you have to be, the product should be pakka characterized. Next is fission products. So fission products, so we are removing from the uranium plutonium. The fission products, maybe you can stop here, ma'am, actually. You can stop here. Right, now fission products, you can see actually fission product, as I said, uranium, plutonium is removed from the spent fuel. Now fission product, cesium, strontium, americium, technetium, ruthenium, These are dominant fission products, what I'm saying. Apart from that, the fractions of so many fission products will be there, right? So now, for example, like our home waste only. So we have to properly tie it and keep it for some when proper place, right? Otherwise, maybe if dog comes, it will be spread all over the state. Not look like okay. So if it's small waste, like whatever the waste, biodegradable waste also is look like this way. We have to be very careful. If you talk about fission products, for example, I'll say strontium 90. I told, maybe you can remember strontium 90. In our body, we are having a more amount of calcium, right? So the calcium and strontium almost near in the periodic table, right? This calcium, if some amount of strontium goes inside your body, that strontium can easily replace calcium. The strontium off life also I told 30 years. So it will be replaced and it will go in your body. It will be in 30 years. 30 years it will emit very high energy beta particles. That beta particle affect you like anything. So based on the quantity also matter actually. So that's how we should not just like that throw it. Another option, another example, technetium. Maybe you know actually technetium, some maybe heard about it, technetium 99M. So technetium metastable yam that will be used. PET CT scan, if you see all the centers, they are using technetium 99M. That off life is 6 hours. So they will be given to you actually. It will go and sit where the cancerous cell or whatever the foreign body in your foreign cells in your body, it will be locating that radioactive elements. The same case, technetium 99, it's not metastable. Technetium 99, that off life is 2.5 in 10 power 5 years, which means maybe 2,50,000 years. So millions of 2 million years of life. If that goes actually, it will also go and sit where the technetium 99M, because isotopes may be different, but chemical property will be similar. It will go and sit in somewhere. It will affect, right? It will be giving more problem to human race. Not only human, if we are allowing into the sea or some plant or soil, it will go and affect all the organisms, right? So whatever that uranium plutonium removed, the spent fuel, we should be very, very carefully handled. The fission product. So after that, the fission products we can classify it as based on the activity, based on the off life, as well as the based on the physical property, like solid or liquid or gaseous. So liquid, if we take actually, it will be, we can classify as low level waste, intermediate level waste, high level waste. Now high level waste in the sense there only every radionuclides will be there. So now, so I want to put this high level waste or whatever the toxic radiotoxic elements in safer place. Safer in the sense it should not move after that. So I have to freeze it. So how to freeze? So lot of research is there in the field actually. The people finally comes out of that. For example, if you take Egyptian pyramids or some other places actually, still that olden history, some of the things are still intact. If you take a glass, right? Maybe maybe I remember when in my village side and all, if I see glass pieces or something here and there, after a year also, after 2 years also, maybe it will be there is not be degradation. It will be stable actually. So finally they found out that glass is the stable material, right? Glass will not affected by sun or rain, whatever maybe, it will be stable material. So we will put everything in the glass, right? Inside the glass. It's not a glass bottle, inside the glass. So how to do it? So that's why that process is called vitrification. Vitrification is meaning is making a glass. So now, Ron, you can play, ma'am. Play the video. Now the fission products and the base glasses. Glasses based on borosilicate or will be mixed together and put it into that melter with high temperature furnaces. So the both fission products and these fission products, the HLW will be concentrated and mixed together in the base glass, and together both will be melt together, and then you can see here process it and calcined, all nitrate will be goes off and become an oxide, and then finally that calcination will be happen. Finally it will become melt when our radionuclides as well as glass, both will become a melt actually. That melt will pour it into that some stainless steel canisters. You can see here. Now all the radionuclides will be inside the glass. So we made it as a in-cot, some kind of glass. We can see this. This is how we can pour it in the SS canisters. So radionuclides will be there immobilized in the glass. So this will be almost minimum of 500 to 1000 years will be intact. So for example, can you stop here, ma'am? So please stop, ma'am. So actually that after that, so now cesium, strontium, I told that is a major one. Half-life is 30 years. So 10 half-life is 300 years. 300 years, after 300 years, will not have any heat. So after 300 years, we have to worry about only that alpha radionuclides, for example, uranium and plutonium, whatever the fraction comes out of the reprocessing, that only be very problem. Then americium also, 400 years half-life. Those things will be taken care. Will be the glass will be intact. So finally, the Waste Management Society decided that glass will use it as a host material to immobilize all the radionuclide present in that HLW. So next you can run one. Next actually, whatever that when you dissolution time, if you saw hull is made up of zircaloy. So that hull will be, we have to process it, we have to safely dispose the hull also. Hull will also having a lot of activity that will be washed with different process will be there. The hull will wash with nitric acid, N pieces and separation and dosing. Then it will be compacted. This is how the hull will be immobilized. You can see the volume reduction, you can see almost 5 to 6 will come. Even similar way in vitrification also volume reduction around 10 volume reduction will be there. So now the hull and N pieces will be compacted and made it as a same like HLW canisters. Vitrification, this also made it as a canisters. So now this canister separately as well as HLW poured vitrified mosses as a different canisters. These two will be, we have to think about long-term management. So it will goes to the deep geological repository. But in every country actually, the deep geological repository is still not decided yet. No, actually we are not stopped here. But anyway, I will talk. So that repository is not decided yet. In India also is not decided. So we are making it and we are having it in Kalpakkam itself. We are having it in-dream storage. Actually around 300 years we have a provision. We are having a if you Google it, you can see the Russian doll. We'll having a Russian doll means actually the multi-barrier concepts, right? Similar way the multi-barrier concepts existing, whatever the design engineering design we made it, that this waste will be stored in-dreamly here for almost 30 to 300 years. Then it will be taken to deep geological when places decided. So apart from that, so for example, apart from that, this is the normal presently what is going on all over the world as well as India. Apart from that, recently what we are developing it is going on in progress is actually what I told, there is some radionuclide, cesium, strontium or ruthenium or whatever, americium, everything. If you take about radiotherapy, right, cobalt-60, I told that the half-life is around 2 to 5 years. The similar way, cesium-137 is 30 years. If in the place of cobalt-60, if you replace cesium-137, so your process will be almost 30 years, no need to disturb at all, right? So that's for that actually, cesium is plenty is there. Cesium generation, cesium-137 generation in the reactor, in just like that, in normal things is not possible. But it's coming in the fission reaction is more abundantly. So we don't want to put it into that deep geological. So you want to retrieve back the cesium-137 by using solvent extraction or some method. And then we made it as some kind of not only cancer treatment as well as food irradiation. Now you can see actually all the food, whatever we are getting it is irradiated food. Even blood also after irradiation only it will be given to. For all the purpose actually that cesium-137 can be used. For that already is demonstrated in BARC. cesium-137 is retrieved back from this waste, as like uranium plutonium will be used for the future reactors. Cesium-137 can be used in the medical field as well as normal food irradiation, all the kind of things. So another one thing, strontium-90, I told actually recent article what I read it actually. So our recent Chandrayaan things are happened. So they are saying actually that proper energy source is not there. Strontium-90 is a very high beta energy it will give actually. They are thinking about strontium-90 as a battery. So we'll make a strontium-90. For example, now whatever that satellite goes to the sky or something, they are using plutonium as a energy source. So plutonium anyway, making a plutonium is difficult. Reactor we have to run it. Strontium-90 already is there actually. Well, we can't retrieve the strontium-90 also and use it for further some other purpose. Similar way, now strontium we can retrieve back from that HLW and use it for daily usage. And similar, another one major radionuclide present the HLW is americium-241. That also can be used as a batteries as well as some other applications are already is there for americium-241. So all these three radionuclides can able to extract. So there is no problem for even disposal or nothing actually. Everything we can reuse it. Right, in that way actually this may be advanced fuel cycle is developing all over the world. India's forefront is going on actually. So we are in our laboratory and plant also these experiments we are doing it, extracting radionuclide for our societal applications. Even ruthenium-106 can be used for eye cancer treatment kind of. So all the applications are known now, already demonstrated also extraction and reusing it. So this way, this how advanced fuel cycle, whatever you are mining and taking in uranium and finally put it into that some kind of waste actually, whatever you are taking, everything will be will utilize it. So no need to put all the waste. If I put all the waste into that dump yard or deep geological, maybe after 300 years or 500 years, the future generation will be having a problems. So they have to retrieve back and they have to find out what are the way to treat it again. So if you retrieve now itself and reuse it, another one way we can do it actually, how to convert it actually, the transmutation. So if you give more, if you put into the reactors again, some of the radionuclide, how long-lived radionuclide put into the reactor again, it will be converted to short-lived again. So technetium-99 became a ruthenium-100. Ruthenium-100 will having a half-life of a fraction. So technetium-99 plus one neutron, if you give one neutron, it will be ruthenium-100. So it will be short-lived. Compared to technetium-99, that half-life is very small. So this way also transmutation is there. Transmutation is so that for that. So reactor concept is completely different, but the extraction and reuse societal application will be easier for us. So in both the way that present nuclear waste management is on progress. So I think I've covered most of things. I take this opportunity again. I thank everyone for this wonderful opportunity. If any queries, please mail to me. I'm happy to reply. Thank you, everyone.
Thank you very much, sir, for your wonderful presentation and very informative talk. Actually, we have very good comments from our participants, sir, and
Yes,
we have very many questions from waste disposals. Shall I ask?
Yes, ma'am. Sure.
Okay. How to calculate energy released during nuclear fission reaction?
Yes, ma'am. Actually, calculation is there. For example, that is again comes to E equal to mc squared only, right? So residual mass, right? If uranium-238 breaks down to barium to krypton, some mass will be missed actually. So exactly will not match. So that mass, from the mass we can calculate energy. For that energy only I mentioned around will be 150 to 200 mega electron volt will come for a single reaction. For one atom of uranium-238, 235 undergo reactions. That we are having a calculation. Maybe I'll send you also, ma'am. This is how we can calculate the residual mass, which means residual mass we have to use it for the calculation.
Okay, sir. Okay. And what are the safety measures to dispose this waste radioactive materials? This is the
Yes, ma'am.
This is the question asked by many participants, sir.
Sure, ma'am. So actually, ma'am, radioactive material, for example, I said short-lived and long-lived, right? So short-lived things, actually short-lived means very small half-life. For example, if some radionuclide antimony 125, that half-life is 2 years. So half-life 2 years means 10 half-life. We will having a calculation 10 half-life completely, which means if it is there 10 half-life, after that we no need to worry about the radioisotopes. So 10 half-life means, so if it lesser half-life, so we'll make some host like based on cement. So if cement, we'll take it as a host. So we'll make it as, we will add it with some additives into that, like vermiculate, some kind of inorganic additive. So some absorption medium. So the antimony or not technetium, antimony or ruthenium also 1 year, 365 days only. 1 year kind of radionuclides will be cemented. If its half-life is very high. So if I said cemented, actually the cement we have to characterize after that. The leachability of radionuclide should be, it should be 10 power minus 5 or minus 6 gram per centimeter square. Leach rate should be there. So after that only the product will be qualified for disposal. Similar way, glass also, the vitrified glass also, the leach rate, compressive strength, or if it is dropped from the height, it should not form very repository, like a very fine form. So a lot of characteristic methods are there. So after the characterization only, we will decide that this can be immobilize it.
Okay, sir. And another question is, when nuclear fission reaction occurs in space, why no waste is there?
Where it is happening, ma'am?
In space.
So how we know actually no waste is there?
Okay. Then
No, actually,
why?
which means the gravity will not be there. We can't see anyway. Everything will be floating there only. Is the whether is
Okay.
nuclear waste is there or not? We don't know. Any fission reaction, the product and residue will be there.
Okay. Why radioactive elements used for various fields?
Yes,
Why
ma'am.
it is
Actually, for example, ma'am, if you want to weld, for example, welding or whatever may be, even analytical method also you can take spectroscopy or something. So you should have some gram level to find out, gram level or milligram level to analyze it, right? For example, radioactive material, if you spike or if you do with any method, actually, even I said radiotherapy, scanning or PET CT, everything, actually, the radiation will be very, 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 even 10 power minus 7, minus 10 also can be detected very easily. The detection is very easier compared to non-radioactive elements. That's why the radioactive isotopes can be used in various fields. For example, sensors as well as medical field. As I said, actually, even medical field or irradiation field, a lot of things radioactive having a lot of applications. But we are not exploring much because we are fearing about radioisotopes.
Okay, sir. And the next question is, does the nuclear waste ever go away? Does the nuclear waste ever go away? However, where is the nuclear waste stored?
Yes,
Where
ma'am.
is
Go
that?
away means in the sense, actually. No, go away means that's why we are immobilizing it. So we will not allow anything to go out of that glass or whatever thing, actually. So
Okay.
storing in the sense, that's why final, now the first barrier is glass. The radionuclide first barrier is glass. After that, yes, the canister will be there. After that, that multimeter I told them, a lot of barriers will be there. So radionuclide, it's not possible to just like that leach out and go to the atmosphere, environment. So that's way that way that plan will be there, engineering plan will be there. If it goes also, that's why there are a lot of studies also mentioned, leachability studies, compressive strength or glass transition or temperature increases, whether something comes out or not, glass can break or not, or what temperature. Lot of study before we are putting in the glass. After putting into the glass also, the product characterization will do it. So nothing will go out of that fission, whatever that product immobilized.
Okay. Okay, sir. Then any other radioactive elements can be used for nuclear fission other than F block elements?
F block element, actually, no, ma'am. for my knowledge, is not possible. Possible in the sense, actually, uranium, plutonium, maybe you know now that stability curve of the elements. So most of the block elements will be undergoing fission reaction. Even a block elements also, selective radionuclides only undergo fission reactions.
Okay, sir. And another question is, how can we recycle nuclear waste to make it less toxic to living beings?
That's the thing. Actually, the last part
Is
of
there,
my talk I told actually.
oh, yes, sir. Is there any problem in disposing that? Do we
No
have
problem
any
in the
problem?
sense. No, in the sense, if I straight away dispose it, actually, lot of wealth. Now the concept comes based wealth from the West. The why out to this wealthier, this much costlier. Even there, somebody saying americium a gram will be some lakhs of rupees. So why out to just like that dump it somewhere? So we retrieve back and reuse it. Reuse in this a societal application. As I said, medical as well as food as well as treatment. A lot of application is there. That's why there is no problem. We will try. We will possibly will store it. Should not go out kind of cancer. But still, we will come for advanced treatment method to retrieve and use all the radionuclide comes out of the fission reactions.
Okay, sir. Suppose if a person is exposed to the radiation, what are the methods to decontaminate that radiation, sir?
Yes, ma'am. Actually, that it's maybe everyone know alpha, beta, gamma. Right now, ma'am. Alpha, anyway, it's not possible just like that getting affected by alpha, because the alpha can be stopped by paper itself. But mostly the beta and gamma, the high energy beta, high energy gamma can affect you. The as you asked, actually, the way is two way. One from external and another possible internal. If you take internal, for that also procedure is there how to treat. External, as I said, the time is matter actually. How much time you are spending. So if you are for trainee or officer or the contract person, they are having a limit. If you go for AERB guidelines, actually for officer, you say 6 millisievert per year. 20 millisievert per year is allowed actually. If that is the total will be 100 millisievert is okay for 5 years. If 1 year maybe I am getting 30 millisievert, next year we will adjust it. No need to do much of active work. So then that way the 100 millisievert for 5 years for officers is allowed. So we have to nobody is achieved that much still. Maybe very less only we are exposing.
Okay.
Then internal means actually plutonium or americium alpha or something goes will give some complexing agent inside. So even all the medicines also for the complexing agent we can give. It will be complex for strontium or plutonium will be complex. It will be taken by urine way or some way it will be come out of it. That is also procedure is there.
Oh, okay, sir. Thank you. And the final question is, how do we ignite the fuel in the reactor?
That is for that actually neutron source will be there. Neutron source made up of first reaction will be we have to provide everywhere actually that we have to give the spark. So fuel will be there. We have to provide the neutron spark. For that, I think lithium, aluminum based some material will give more neutrons. So the N alpha reaction, some reaction will be we have to carry out before fission reaction. It will give more neutron. The neutron will go and hit uranium 235. But everything like a probability only in the nuclear reactor. But as I said, if a moderator is not there, the neutron will not go and hit that uranium 235. It just pass only. The moderator will be slow down the neutron, then it will go and hit it. So for that reason, one neutron generator will be there to start the reaction.
Okay, sir. And a final question, sir.
Yes,
How to
ma'am.
calculate a lifetime or period of half-life period of the different radioactive material?
Yes, ma'am. Actually, for every radioactive element, specific activity will be there. So it's like lambda equal to 0.693 divided by T of.
Yeah.
So some formula will be there right now, ma'am. Using that one, if you know the decay constant, you can find out the half-life of all the radionuclide. For every radionuclide, decay constant will be different. Decay constant will be there. If you know that decay constant, for decay constant also some formula will be there. So decay constant you can calculate, then half-life you can calculate for all the radionuclides.
Thank you, sir. Thank you very much for your well-explained answers, sir.
Thank you,
We are very much enlightened. And as a token of appreciation, we would like to give you virtual appreciation letters from our organization, sir. Please be
Thank you,
kind
ma'am.
enough to accept it, sir.
Thank you, ma'am. Yes, ma'am. Yes.
Can you post that appreciation letter, ma'am? Can you post that, ma'am? So this is our appreciation letter, sir. Kindly accept it, sir. And
Yes,
we will mail it, sir.
Okay, ma'am. Yes, ma'am.
Thank you very
Okay,
much.
thank you, ma'am.
Thank you, sir. Thank you. And
Thank you very much.
okay,
Thank
sir.
you, ma'am.
Thank you. Since we have reached the closing phase, I request Mrs. Jeevaratinam, Assistant Professor, Department of Chemistry, to propose vote of thanks. Over to you, ma'am.
Jeeva ma'am, are you there? Okay, I think due to technical error, she is unable to join. Okay, right, I think she's back. Jeeva ma'am, unmute your mic and talk, ma'am.
Jiva ma'am, now you can speak. Please unmute and speak, ma'am. Mrs. Jeevaratinam, yes, please. You can go ahead. I think she's not audible. May I request the head of the department, Dr. Swalyami, to give vote of thanks?
Okay, due to technical error, I think Mrs. Jeevaratnam is unable to join us. So on behalf of the Chemistry Department of Dr. MGR Educational Research Institute, I would like to thank all of you, those who have attended this FDP. And mostly I just wanted to thank our management staffs like our Chancellor, President, Vice Chancellor, Provost, Pro-Vice Chancellor, Register and Joint Register, HNS, etc. And also the dignitaries of our campus, like Joint Register, Dean and Deputy Dean, and also our Dean Chemistry, Mrs. Udekala. I just want to thank Dr.J.Selvakumar, who has given a very energetic presentation. I think, sir, most of the comments are very nice. Everybody had given that your presentation was very good and the explanation was extremely nice. I think we should feel proud to have you with us. Thank you, sir, for your nice presentation. At the last, I would like to thank all the participants for being patiently watching this video as well as listening to the presentation of Dr. J. Selvakumar. Thank you to all.